Okay, today we're talking about rational expressions, which means fractions, right? So domain are all possible x values. So we are talking about the x values in a graph, all the possible ones. So kind of an interval of x values. So like in this problem, if you see this denominator, I'm hoping that you see like x could really be anything, except there's one value that would be a problem, right? So in other words, the domain on this problem is all reals. X can be anything, except there's one value for x that would not work. If x was 5, and the way I got that is I took the denominator and I set it equal to 0. So you add 5 and you get x equals 5. So x actually can't be 5 because if x was 5, 5 minus 5 is 0. You can't divide by 0, it's undefined. So it's pretty quick. You could look at the denominators of a problem and figure it out. So if you had something like 1 over x plus 3 times x minus 2, what's the domain of that guy? So the domain would be all reals, except x cannot be actually two different values here, -3, and x can't be 2 for this particular function or expression. Let's see. So let's look at this one. So this next one, look at the denominator. What would happen if x, is there any value for x that would make the denominator equal to 0? Well, there's no way to make the denominator equal to 0 there, so the domain is all reals. Lots of functions have a domain of all reals. There's no restrictions. Now, square roots also have some restrictions. So denominators we talked about affects the domain, but also square roots because, remember, we've talked about this already this year. What's the square root of -4? Well, it's not a real number. It's actually 2i, but it's not real, right? We can't actually do that one. So think about a value that you could plug in there for x that would make that denominator negative, that make that square root negative, which would make it imaginary, right? So I'm thinking if you plugged in -3, that's not going to work out well. -4, -5, -6. There's a whole bunch of values that don't work. So what we do with this particular setting is we basically take whatever's inside of there, that's called the radicand, and we set it greater than or equal to 0, because I'm actually fine with that radicand being bigger than 0, being positive. I'm also fine with it being 0, because square root of 0 is 0. I just can't have that negative. So it has to be bigger than or equal to 0. So if I subtract 2, I get x is greater than or equal to -2. Which kind of makes sense, right? If you plug in -2, that works. That's 0. Plug in 3 plus 2. I mean, actually -1 is square root of 1, which is 1. So all those values work. So that's the domain of that particular function. Cube roots don't really have any restrictions. And the reason is I could, like square root, again, square root of a negative causes problems. That's going to be imaginary every time. We don't know about those, but we know square root of negatives do that. But cube root of a negative, for example, can you take the cube root of -8? Well, yes, the answer is -2. -2 times -2 times -2 is a -8. So I have the same number, -2 to the third power is 8. So because of that, you can take the cube root. So this is all reals. Cube roots have no restrictions. Square roots, maybe I should say it this way. Even roots have restrictions. You'd have to use this method. You'd have to set it greater than or equal to 0 and solve it. Odd roots have no restrictions. The domain is going to be all reals for all of the odd roots. Okay, so this one has a bunch going on here. So first, let's look at the denominator. So if you look at just the denominator, you would say the domain is all reals, except x cannot be 3. And for the next one, you'd say for this one, you'd say, well, take the radicand and set it greater than or equal to 0. That's actually the domain of that one, and this is the domain of that one. So let's meld these two things together. So let's try this. So if you kind of graph this, let's see, 3 and 0. Up above, I'm going to graph x greater than or equal to 0, something like that. I'm going to graph all reals except at 3, it's like an open circle, and it goes everywhere. So we have to think about, we talked about and or. So in this statement, so the numerator, has to be basically the domain is all those green values there. The denominator are everything except for 3, all the blue graph numbers. So if this function's domain, I have to consider both the green and the blue. So I think this is an and situation here, not an or situation. We need both to be true in order to be part of the domain. Otherwise, it's restricted for part of the problem. So everything here seems to be overlapped. Everything here there's just a little discontinuity point right there. So I think your answer would be something like closed circle at 0, open circle at 3, and it goes right. So this is really, I guess if you're going to write this, this would be technically 2 different intervals. And here's what I mean by that. So if I'm going to write my answer, first I'm going to take the interval from 0 to 3, so 0 to 3. And then I'm going to take the interval from 3 to infinity. And we're doing the intersection or union of the 2, I guess, union of the 2. Or you could say 0 less or equal to x less than 3, or x greater than 3. That would be acceptable as well. So either one of those answers, if you wrote them out, would work there. From a graph, maybe it's easier, I'm not sure. But if you think about like this point, it looks to be at 0, comma, -2, and the graph seems to go up and to the right forever. It seems to have a pattern of going up and to the right for all time. So for this graph, the domain is going to be not all reals, because think about this whole area over here, right? There's no points over there. There's no graph over there. It's just kind of empty. So x really can't be negative, because that's all those values are where x is negative. X could be 0 or above. So I would say the domain is going to be x greater than or equal to 0. Or you could say 0 bracket, comma, infinity. That would be acceptable as well. So factoring and then cancel. So the concept, before we get to actual problem, this is the concept, which is, if you have multiplication there, if that's multiplied, it'd be a times c and b times c, the c's just cancel out nicely, and you just get a over b. I know you know that property. So here, there's really 2 steps to this. First thing is factor. Factoring shouldn't be too bad here, at least it doesn't look like on this one. So the numerator would be, I guess, x plus 3, x plus 1. Looks like that works. And denominator difference of squares, hopefully you see it, so it'd be x plus 1 times x minus 1. And those are time sign technically in between those 2 factors there. So you can only, so first you have to factor. So we took out, we factored both things. And then the fun part, right? What's the best part is canceling. It's pretty fun. This is just a limited amount of fun because you only get to cancel one of them. But they are being multiplied, so I can cancel those out. So I do have the answer of x plus 3 over x minus 1. If you wanted to mention the domain in your answer, in this case, the answer would be all reals, but x can't be 1 or -1, right? Because each one of these, that the denominator would be 0 in that case. Even though that cancels out, the denominator still can't be -1 because the original problem is what you're really testing there. So you haven't canceled that yet. Okay, let's look at this one. So this looks like fun, right? This actually is kind of fun. So you're going to factor and then cancel here. So this would be x minus 4 times x plus 4, difference of squares. That's not too bad. X and x, I guess looks like it'd be 4 and 1. The bigger number's negative, okay, so for that -3. So I think we got it. Looks like those cancel, and so you're left with, I guess, x plus 4 over x plus 1. And again, if you put the restrictions on that, all reals, the domain, but x cannot be 4 or -1. I know you know this property, when you have 2 fractions and you're multiplying, you're allowed to, because multiplication, combine those into 1 fraction. So that's the concept we're using here. So the method's pretty much the same. So and the cadence is, factor first and then, if possible, cancel. So everything is being multiplied. So if you factor that first one, it looks like it's going to be, I guess, x and x, maybe 3 and 1. And the bigger number is positive, so I think that's it. I don't think 3x plus 2 really factors there, so I'm going to leave that. And the first parentheses over there would be factors, it looks like, I'm guessing. So maybe 4 and 4, both positive, and then x minus 1. Everything cancel. Ooh, this is kind of disappointing. Only one thing cancels, right? So then I guess you would write your answer, I guess it'd be x plus 3 times 3x plus 2 over x plus 4. I guess squared, I could just write squared there. So x plus 4 quantity squared. If they ask about restrictions, x or the domain, x cannot be, so x can be all reals except for -4 and 1, right? Those are the two restrictions. Okay, so we're doing real well here. So let's get this one. Okay, so on this one, when you divide, I think we have actually talked about this one, right? When you divide by a fraction, you multiply by its reciprocal right there. So you'd multiply by d over c. So when you first see this problem, one of the first things you might want to consider doing is actually just flipping the fraction. So here's what I mean. So let me take this one. So this key is that division there. So that's gonna that separate second fraction is gonna flip or reciprocal. So this one, it looks like a factor is that would be 2y plus 3 times 2y minus 3. It's kind of like difference of squares, just a little tougher, right? It's difference of squares. Denominator, ooh, looks tougher. It's not going to be easy, so maybe 2y and y. I don't know what's going to work here. You can guess and check this. Let's see, I'm trying to do some in my head. Maybe 6 and 3, I'm just guessing. So no, let's see, 6, 3, 9, and 2, 18 and 1. So I'm not sure. Okay, let's try this. 3 and 6. So let's see, the bigger number is positive. So if that's it, I guess this one would be positive. This one's negative. It'd be -3y plus 12y. That works. Okay, phew. Wow, it takes a while to do some factoring guess and check method. Okay, so this one's going to flip, right? That's the big key here. So I'm going to put, let me put this bottom one up on top. That's easy, somewhat easy to factor here. So y. I guess it'd be 6 and 1. The bigger number is positive. There you go. And then you're going to factor the denominator. So that would be 2y and y. So it's either 3 and 1 or 1 and 3. I'm just going to try this one and see what happens when I plug that in there. So that would be 1 and 6, which does not add up to that one. So let's try this way. How about this? Just going to try different options there. So the bigger number is positive 1 is positive there. So I guess this would be plus and minus. Let's make sure 3y minus 2y is 1y. 3 times -1, that works. Okay, I've got it all factored. So now this is times. Again, because I did what? I flipped that fraction. It's very important. So in this one, what cancels? This is all being multiplied, so I can cancel here. Ooh, this is kind of fun. Y plus 6 cancels. 2y plus 3 cancels. Oh, this is like amazing. 2y minus 3 cancels. Oh my goodness, everything cancels. When you cancel, you leave behind a 1. So essentially the answer for this one is 1. So it actually does kind of work out there.